today we're going to learn how to use KC to figure out X, basically. All right, it's just like I said, it's going to be just like what we did if you were to look back at the notes from the KC stuff from last chapter. Now it's just solving for KA, doing the same things. I showed you last period how to do the KA solving when you're given enough information to figure out what the hydronium was, either through the pH or the percent ionization. This time, I'm going to give you KA and ask you to figure out X. Okay, so it's backwards. And this first one's going to have everything on it. Matter of fact, it'd be very difficult to fit it all on one board, but I will probably have to erase a little bit, but we'll do most of it on one board. But notice what I'm asking you for. Basically, hydronium, hydroxide, pH, pOH, percent ionization, all that stuff comes from trying to figure out what X is. Because here's Ka, it tells you what Ka is, and it tells you what the concentration is. All right, well, again, we're going to use a generic monoprotic acid, HA plus H2O yields hydronium and whatever the negative ion is. You know, even these are done by I, C, and E. And not even these, but especially in these. My initial concentration is 0.100 molar of that. I don't care about water. He's constant anyway, 0 and 0. This should all be very familiar to you by now. 0.100 molar of this minus, sorry, getting ahead of myself. Getting ahead of myself. Minus X, plus X, and plus X. Because he's got only one direction he's going to go. I've got reactants and no products. 0.100 minus X, X, and X. Okay, none of this is surprising. The difference is, from the previous two examples, I don't know what X is. I have no way of figuring it out and then solving for Ka. I'm given Ka. So, what do? I set it up. And what's going to be nice is coming up in a minute is a real nice hint, or not hint, trick. Ka equals, got to show me the equation. Hydronium times the A negative, whatever he is, over HA. I know the Ka is 3.50 times 10 to the negative 6 equals X times X over 0.100 minus X. Now, before you grab your calculators and start reaching for the quadratic formula button, you're not going to need it. Nope. Believe it or not. You would. Normally, what I would have to do is I would have X squared, multiply it, distribute that, and I'd have to get all the variables on one, 0 on the other, right? I get all that stuff in the form of a quadratic equation, plug it in, get my two roots, figure out which root's correct, then plug them back in for X. I don't have to do that here. Watch this. Check this out. All right? And I need you to listen to this because I'm recording it, I'm not going to have you read. I want you to read it in a little bit. At the end of the period, I'll have you read where it explains why mathematically this works. But I'll just be able to explain it to you right now. I know by definition a weak acid has a very small Ka. And that means that very little of this becomes hydronium ions. Very little point of the 0.10 molar becomes hydronium ions. So how big is X? Very small. Very, very, very small. If this number is times 10 to the negative 4th or smaller, you can pretty much ignore how much X is subtracted away from that guy because he's so small. Negative 4 or smaller for that guy. And if this guy over here is 0.05 or bigger, it's like taking don't do this, 0.100 molar. Well, you're going to end up subtracting away from that a number something like 0.00005 or something like that. Now, if you do that and you subtract it, you're going to get 0.09999. So that in the significant figures, what are you going to round that up to be anyway? 0.1. It's going to be the same number. All right? So you're going to basically ignore X. You're going to ignore X. You can write that down.
Just on the bottom.
just on the bottom. That's a good. Somebody else asked the same question last period. Why don't you ignore x everywhere? Well, there's two reasons you can't ignore x everywhere. One of them would be if you ignored x everywhere, you wouldn't be solving for anything. All right, so that'd be one. But that's not. That doesn't really explain why. Let me explain why. The reason you can't ignore x, I can't normally ignore a variable. I can only ignore a variable if he's being subtracted from a very large number so that it won't make a difference. I still have to solve for what that small number is. That small number doesn't go away. All right, so if I get, but what's nice about this, if I get rid of that x, watch how easy this problem becomes. I'm simply going to cross multiply, and I will get x squared equals 3.5 to the negative 6 times 0.1, which is 3.50 times 10 to the negative 7, right? I think. And then what do you have to do? What do you have to do now? Just take the square root, right?
Right.
What's the square root of 3.50 times 10 to the negative 7? 5.92 times 10 to the what?
-4.
Negative 4. Okay? So like I said, x is such a small number. If you had done this right at this point and not ignored x and gone through the whole thing, you would have gotten pretty much the same number. It may have been slightly different because but when you rounded it off to the significant figures, it would have come out to be virtually the same number. And you can do that as long as this guy's small enough and this guy you're subtracting him from is big enough. You see why both of them have to be in place. If I have just because x is very small, what if my concentration was 0.000001? Then it would matter that I subtracted away that, you see? So I do have to have both a very small Ka and a relatively large, obviously 0.1 is not a big number, but a relatively large compared to this guy. And the cutoff points you're going to read in that little box I'm going to tell you to read on page 766 in a minute are -4 for that guy or smaller, which means -5, -6, -7, and 0.05 over here or bigger. All right, and that will be the case for all of your homework problems and all of the test problems. So you will not have to use the quadratic. You won't have to borrow those calculators again. Okay, isn't that nice? All right, I'm still not done. What do I have to do now? I have a heck of a lot to do actually. I have hydronium, hydroxide, pH, and POH, and a percent ionization. Which one of those 5 do I know?
You know the hydronium.
I know the hydronium. This is the hydronium.
Awesome. Sweet.
Which is nice because if I know the hydronium, how do I figure out the pH? Yeah, pH is just a negative log of the hydronium, which is the negative log of 5.92 times 10 to the negative 4th. So the pH, you have to do that on your calculator, is what? 3.23? Okay, it's 3.23. Let me stop there for a second and say a few words about that. What would the pH have been if this had been a strong acid? Look what his original concentration was. Yeah, so the pH would have been 1, a very, very acidic solution. This is only 3.23. It's nowhere near as acidic. Okay, the higher the number for acids, the less acidic it is. How do I get the POH? That's easy enough.
Subtract 3.23.
Which will give me, what, 11.77? Is that right? 10.7. I can't subtract in my head. 10.77. So there's your POH. Right? I still have to get the hydroxide. I can do that 2 ways. I can take the inverse log of, that's what I'm going to end up doing. No, that's not true. I'm going to end up, I could take the inverse log of POH, or let's just do it this way because that's the way we usually do it. Okay? KW. When there's trouble, you call KW. KW equals hydronium times hydroxide. I know the hydronium. I'm going to figure out the hydroxide. So the hydroxide equals KW over hydronium, which is 1 times 10 to the negative 14th molar squared over the hydronium, which was 5.92 times 10 to the negative 4th, or 0.000592. What do you get for your OH?
1.69 times 10 to the negative 1.
Okay? 1.69 times 10 to the negative 11?
Yep.
All right. I'm almost done. I have one last thing to do, and that's the percentization. Like I said, I wouldn't have room to fit everything up here. So I'm going to have to erase. I'll erase over here. How am I going to get percent ionization while I'm erasing this? What do you think? Think about what percent ionization would probably mean. Okay? Percent ionization means the percent that broke up from that 0.10 molar. Now, how do I get, I know the amount that broke up is X. That's how much that actually became hydronium. So if I know that X is 0.000592, and that's the original amount, what do I do to get a percentage of anything? What's my formula for percentage of anything going back to Chem 1 when we first started talking about percentages with percent error, percent composition, percent of people in the class, percent on a quiz? What do you do every time? Part over the whole times 100. Exactly. That's your formula every time. The part that broke up is X. The whole that it came from is that, right? So basically percent always equals part over the whole times 100. All right? If there were 5 girls in the class of 10 people total, 5 over 10 is 50%. 5 over 10 times 100. So in this case, it's going to be 5.92 times 10 to the negative 4th, over 0.100 molar times by 100, and I should get, well, what will I get? I'll make this guy bigger by 1 here, then I'll make him bigger by 2 more, so it'll be 0.592, right?
Yep.
Is that right? Okay, so you're 0.592% broke up. That's a very small amount, but that's not surprising considering it's a weak acid, and by definition, a weak acid doesn't break up a whole heck of a lot in solution. All right, now the homework for tonight I want to put up here for Lizzie, who said to make sure you put the homework up every night.
7 problems. That's crazy.
Yeah, but then you got the rest of this period and some of probably tomorrow too. There's the homework for tonight.
Are we getting more homework tomorrow?
I don't know. We have a single tomorrow, right?
Yeah.
I'm not sure.
So